friends. Now I am taking class on elementary signals. Again, you have here continuous time elementary signals and discrete time elementary signals. We have few elementary signals here. First one is exponential signals, sinusoidal signals, exponentially damped sinusoidal signals, unit step function, unit impulse function, and unit ramp function. You see that exponential signal, first one, continuous time exponential signal. Any continuous time exponential signal is given as x of t is equal to c into e to the power of at, where c and a are the constants. Where c indicates the amplitude and a is also some constant here. Depends upon value of a, we will get the growing exponential signal and decaying exponential signal. If a is greater than 0, that is exponential signal looks like this. Okay, this is the t, this is 0, this is the x of t, that is equal to c into e to the power of at. When t is 0, x of t c into e to the power of 0 value is 1. This is c. That means as time increases, that is x of t increases. That's why we'll call this as a growing exponential signal. Okay. Suppose if a is less than 0, okay, that means if a is -1, -2 like this, then we have a signal that is a decaying exponential signal, that is represented like this. This is the decaying exponential signal. This is t, this is 0. When t is 0, its value is c. This is the x of t is equal to c into e to the power of t. See, continuous time exponential signal he is given as x of t is equal to c into e to the power of at. Depends upon value of a, will get the growing or decaying exponential signal. If a is greater than 0, we'll get the growing exponential signal. If a is less than 0, we'll get the decaying exponential signal. Okay. This is about the continuous time exponential signal. Next is sinusoidal signal. Second one is the sinusoidal signal. Sinusoidal signal. Sinusoidal signals are represented as x of t is equal to a into cos of omega t plus phi. Okay, so cos of omega t plus phi, or you can take sin of omega t plus phi, where a is the maximum value, that is the amplitude indicates, omega is the frequency, t is the time, and phi is the phase shift, and fundamental period of this is given by, that is 2 pi by omega. These sinusoidal signals are represented like that, is these are the sinusoidal signals. Okay. Third one is exponentially damped sinusoidal signal. Exponentially damped sinusoidal signals. Exponentially damped sinusoidal signal is given by x of t is equal to e to the power of minus at into sine of omega t. See here, if a is greater than 0, we will get the decaying exponentially damped sinusoid. Here, you know that we have a sinusoidal signal like this. This is the sinusoidal signal. This is a sinusoidal signal. When it is multiplied by decaying exponential signal, it will become a damped sinusoidal signal. That is, when this is multiplied with this is the sine of omega t, this is e to the power of minus at, This is sine of omega t. When these two are multiplied, you'll get an exponentially damped sinusoidal signal. Okay. This is about the exponentially damped sinusoids. Next one is we have unit step function. That is unit step function. What is unit step function? A continuous time unit step function is defined as u of t equals to 1 when t is greater than or equal to 0 and its value is 0 when t is less than 0. It is represented as its value is 1 when t is greater than or equal to 0 and its value is 0 when t is less than 0. This is t, this is 0, this is the u of t. Okay, this is the unit step function. Next one is unit impulse function. Unit impulse function. What is unit impulse function? A continuous time unit impulse function is represented as del of t. It is defined as del of t equals to 0 when t is not equal to 0 and its value is 1 when t is equal to 0. That is nothing but it can be represented e to the power of minus infinity plus infinity integration of minus infinity to plus infinity del of t into dt, value is 1. It exists only at 0. It is represented as representation of del of t is this is the del of t. Its value is infinity at 0 actually. We are taking this as an unit impulse function. Unit impulse function is an derivative of unit step function with respect to time. Consider a non-idealized unit step function, that is, for example, if you have an unit step function like this, this is the unit step function. See, this width is del, this is the u del of t, its value is 1. When you see that del of t, it looks like an impulse function. This is the del and this is the 1 by del. Area of this is 1. Okay, that is du of t by dt. du of t by dt value is 1. That means as del tends to 0, 1 by del it will become infinity. That's why we are shown with the arrow mark here at 0. That's a unit impulse function is defined as its value is 1 at t is equal to 0 and its value is 0 when t is not equal to 0. The important functions of this unit impulse functions are it has 0 width. First point is it has 0 width. Next is infinite height. Infinite height. Next is it has unit area. It has an unit area. It is derived from the unit step function. Okay. Some important properties of unit step functions we need to know here. That is properties of unit step function. First property is integration of minus infinity to plus infinity del of t into dt, its value is 1. Okay, because it exists only at 0. Next, second property is when it is multiplied by any constant integration of minus infinity to plus infinity, k into del of t into dt, its value is k. Next, if any signal is multiplied by unit step function, we'll get the, that is what is there at 0, x of t into del of t, its value is x of 0, because del of t exists only at 0. Whatever the value is there at 0, that is multiplied with the x of t here. Okay. Next is, if you integrate signal with the impulse function, that is integration of minus infinity plus infinity, x of t into del of t into dt is equal to, that is also x of 0. And next property is, suppose if you multiply the input signal with the delayed version of the impulse function del of t minus t naught, then answer is x of t minus x of t into what is there at t naught, x of t naught, sorry, this is x of t naught into del of t minus t naught. Okay, because del of t exists at 0 when it is shifted by t naught units. What is there at t naught, that value is 1, and what is there at t naught of input signal, that is multiplied here. Okay. And next is, suppose if you have x of, sorry, del of at, when it is scaled by scaling factor a, answer is 1 by a into del of t. Okay. These are the properties of unit impulse function. Next, last one is, we have a ramp function. A continuous time ramp function is defined as r of t equals to t when t is greater than or equal to 0 and 0 when t is less than 0. It is defined as, see, this is the ramp function. See, r of t is equal to t when t is greater than or equal to 0, and its value is 0 when t is less than 0. When t is 0, its value is 0. When t is 1, its value is 1. When t is 2, its value is 2. Like that. As time increases, the r of t function also increases. Okay. This we'll call it as an unit ramp function. See, these are the important elementary continuous time elementary signals. With this, we have other important signals like triangular function, rectangular function. Other important signals are other important signals are other important signals are first one is signum function, signum, signum function. Signum function is defined as sgn of t. Its value is minus 1 when t is less than 0, and its value is 0 when t is equal to 0, and its value is plus 1 when t is greater than 0. The signum function is defined as its value is minus 1, its value is minus 1 when t is less than 0, and its value is 0 when t is equal to 0, and its value is 1 when t is greater than 0. How do you represent this graphically? Its graphical representation is its value is minus 1 when t is less than 0, and it goes to 1 when t is greater than 0. See, this is how signum function is defined. Okay. Next, next important signal is rectangular function. Rectangular rectangular function. Rectangular function is represented as rect of t. Its value is 1 when, that is, modulus of t is less than or equal to 1 by 2, and its value is 0 and modulus of t is greater than 1 by 2. That means outside this minus 1 by 2 and plus 1 by 2, the value is 0. That is, it is represented like this. Rectangular function is, this is 1 by 2, this is minus 1 by 2, this is 0, this is t, its value is 1. This is the rectangular function, rect of t. Okay. Next, triangular function. Next one is triangular function. Triangular function is defined as tri of t is equal to 1 minus of modulus of t. That is, when t is less than or equal to, modulus of t is less than or equal to 1, and its value is 0 when modulus of t is greater than 1. That means graphically it is represented like this. This is t. When t is minus 1, minus of minus will become plus. Here in modulus of t it will be 0. It goes like this, minus 1 to plus 1. Next it plus 1. Plus 1. This is the, at 0 its value is 1. See, this is the triangular function TIR of t. So we have three important signals here. One is signum function, next one is rectangular function, third one is triangular function. Signum function is defined as, that is, signum function is Sgn of t is equal to minus 1 when t is less than 0, and its value is 0 when t is equal to 0, and its value is 1 when t is greater than 0. This is how graphically it is represented like this. Rectangular function, rect of t is equal to 1 when modulus of t is less than or equal to 1 by 2, and 0 when modulus of t is greater than 1 by 2. This is the rectangular function. Next, triangular function, it is represented as tri of t equals to 1 minus of modulus of t. That is, this function holds good when modulus of t is less than or equal to 1, and its value is 0 when modulus of t is greater than 1. Outside the minus 1 and plus 1, the value is 0. Okay, that is, it looks like a triangular function. Okay, and so we'll call it as a triangular function. Next, we have last one, we have a sinc function. It is sinc function. Sinc function is represented as, that is, sinc of t, that is equal to sine of pi t whole divided by pi t. Sin theta by theta, we'll call it as an sinc function. Here, sinc of t is represented as this is t, this is 0, this value is 1, this is 2. Similarly, it goes like this. We'll call this as an sinc function. This is minus 1, this is minus 2. At 0, its value is 1. Okay, This is called sink of t. Okay. These are the continuous time elementary signals and some important signals. Similarly, we can discuss the discrete time elementary signals. Okay, that is, next is we go for the discrete time elementary signals. Discrete time elementary signals. Again, we have same six functions: exponential, sinusoidal, exponentially damped sinusoidal, unit step function, unit impulse function, and ramp function. In the first one, we take exponential, discrete time exponential signal. Discrete time exponential signal. A discrete time exponential signal is given as x of n is equal to c into a to the power of n. C into alpha to the power of n, anything you can take. That is, if a is greater than 1, if a is greater than 1, we'll get the growing discrete time exponential signal. See, when n is 0, it will become value is c. When n is minus 1, it will be less than that. Suppose if I take a is equal to 2, when n is minus 1, it will be 2 to the power of minus 1 will get, that will get c by 2. Next, c by 4, it goes like this. When n is 1, it will be c into a. When n is 2, it will be c into a square. It goes like this. Is the growing exponential discrete time signal. Similarly, take a is if a is in between 0 and 1, if a is in between, suppose if I take a is equal to 1 by 2, in that case I'll get the decaying exponential signal. It looks like this. When it is 0, this is the x of n, its value is c, minus 1, minus 2, minus 3. It's 1, 2, 3. It looks like a decaying discrete time exponential signal. That's a discrete time exponential signal is represented as x of n is equal to c into a to the power of n. If a is greater than 1, it is a growing discrete time exponential signal. If a is in between 0 and 1, then it will be decaying discrete time exponential signal. Okay. Next, sinusoidal signals are represented like this. That is, sinusoidal signals. That is, x of n is equal to a into cos of omega naught n plus phi. A is the amplitude, omega naught is the frequency, n is the time, phi is the phase shift in radians. Okay. Exponentially damped sinusoidal signals are represented. Again, this sinusoidal signal looks like this. Take like this. This is the x of n. That means it is the sampled version of the continuous time signal. Exponentially damped sinusoidal signal is exponentially damped sinusoidal signals are x of n is equal to c into a to the power of n into sine of omega n plus phi. Omega n plus phi. That is modulus of a is less than 1. Next is unit step function. Unit step function. Unit step function is represented as u of n. It is defined as u of n is equal to 1 when n is greater than or equal to 0 and 0 when n is less than 0. It is n, this is the u of n, at 0 its value is 1, at 1 its value is 1, at 2 its value is 1, at 3 its value is 1, it goes till infinity. Okay, this is called unit step function. Similarly, unit impulse function is unit impulse discrete time unit impulse function is, that is del of n is equal to 1 when n is equal to 0 and 0 when n is not equal to 0. It is represented like this. This is n, this is 0, this is del of n, its value is 1 at 1. Remaining all points, its value is 0. Okay, this is the unit impulse function. Next, some important properties of discrete time unit impulse function is the properties of discrete time impulse function. Discrete time impulse function, or first one you can take, that is x of n, it is multiplied by del of n. Answer is, you get what is there at x of 0, x of 0 into del of n. Suppose second one is, that is x of n into del of n minus n naught. That means you get x of n naught, because it multiplies only at what is there at n is equal to n naught. Okay, that is del of n minus n naught. Next is, suppose if we take summation of k, n tends from minus infinity to plus infinity, x of n into del of n. Answer is x of 0 only. Even though you are varying from minus infinity to plus infinity, what is there at 0, only that value is multiplied with the input signal, because del of n exists only at n is equal to 0. Okay. Next property is summation of n tends from minus infinity to plus infinity, x of n del of n minus n naught, that is equal to x of n naught only. Okay, these are the some important properties of discrete time impulse function. Okay, next, unit ramp function. Unit ramp function, that is r of n, it is defined as discrete time unit ramp function is defined as r of n is equal to n when n is greater than or equal to 0 and 0 when n is less than 0. Okay, that is, it is represented like this. This is n 0, this is r of n. At n is 0, its value is 0. When n is 1, its value is 1. When n is 2, its value is 2. When n is 3, its value is 3. When n is 4, its value is 4. 1, 2, 3, 4. This is the unit ramp function. Okay. And similarly, other important functions are same. We have signum function. Other important signals in the discrete domain are other important signals. The first one is signum function, SGN of n. Instead of t, you should use n here. Its value is 1 and n is greater than 0, and 0 when n is equal to 0, and minus 1 when n is less than 0. It is represented like this. At 0, its value is 0. When n is greater than 0, all values are 1s. That is minus 1, minus 2, or minus 1 here. This is the signum function in the discrete domain. Okay. Similarly, next one is rectangular function. Rectangular function. It is represented as rect of n. Its value is 1 when modulus of n is less than or equal to some sample. That is, n naught indicates the number of samples here, and 0 when modulus of n is greater than n naught. That is, at 0 its value is 1, 1 up to plus n naught values are 1s, up to minus n naught values are 1s. This is the rect of n. Okay. Next, last one is triangular function. Triangular function. It is represented as triangular of n is equal to 1 minus of modulus of n by n naught. This holds good when modulus of n is less than or equal to n naught, and its value is 0 when modulus of n is greater than n naught. It is represented graphically as n. At 0 its value is 1. Next it decreases like this. See, it looks like a triangular. This is the triangular, discrete time triangular function. Okay, these are the elementary signals in both continuous and discrete domain. This completes the class. Thank you.